Hello friends, welcome back to Scientific Blunders, where you learn the don'ts first. So today we're going to resume our series on rotational mechanics, and here's the problem we have. A cylinder rolls up an inclined plane, reaches some height, and then rolls down without slipping throughout these motions. The directions of the frictional force acting on the cylinder are A. Up the incline while ascending and down while descending, B. Up while ascending and descending, C. Down the incline while ascending and up while descending, and D. Down while ascending and descending. And for those of you who are curious as to the source of this question, this is taken from IIT JEE 2002. So it's quite an old question. And let's get started. So let me scroll down a little bit. So the first thing we want to do, there's a bunch of words here, but as with any mechanics problem, the first thing we want to do is to draw a diagram, right? And so we have an inclined plane that probably looks something like this, inclined at an angle theta, let's say. And there's a cylinder so a cylinder is going to be, a circle when you look at its cross section. And so the cylinder is rolling up an inclined plane, right? So when it's rolling up, the center of mass of the cylinder is going to move in this direction, and the angular velocity is going to be in this direction, omega, and let's say VCOM, velocity of the center of mass, right? And we want to know the direction of the frictional force acting on the cylinder while ascending and while descending, right? So let's create two cases. So this is when the cylinder is ascending, and we are going to have a similar case for when the cylinder is descending. And so we haven't been given any numbers or any variables here. Of course, we can assume some variables, but we need to find out the direction of the frictional force. Alright, so let me draw a similar diagram for the descending case as well. Inclined at an angle theta, and you have a cylinder again, and this time, and so this time it's going to be, the velocity of the center of mass is going to be in this direction, and the angular velocity is going to be in this direction. So what is the direction of the frictional force in these two scenarios? So that is the question. So let me scroll down further so that we have more space to draw the free body diagram and analyze these two scenarios carefully. So let me start off with the descending scenario, because that tends to be more common for some reason, right? So what are all the forces acting on the cylinder? Well, we have the weight mg, we have the normal reaction n, and we have the frictional force, but we need to know the direction. So let's try to understand what would happen if there was no friction, right? This cylinder is going to tend to slide downwards, right? So the motion of this point has a relative tendency to move in this direction, right? So frictional force is going to oppose that, since friction always opposes the tendency of relative motion, and so frictional force is going to act in this direction, right? And these are the only three forces on the cylinder, but let's just make sure that we have written the equations correctly. And so what we can do is to resolve the mg along two components. So this is going to be mg cos theta, and this component is going to be mg sin theta. And although all we have to do is find the direction of frictional force, but I like to write these equations just to make sure everything makes sense. So in this dimension, the acceleration of the center of mass is 0, which means the net force must be 0, which means n must be exactly balanced by mg cos theta. And in this direction, just intuitively speaking, the center of mass is going to accelerate in this direction, which means mg sine theta minus f must equal m times the acceleration of center of mass. So this is one equation for this direction, the second equation for this direction, and remember there's a third equation from the rotational law of motion, right? And that is that the torque about the center of mass will be equal to the moment of inertia about the center of mass times alpha, which is the angular acceleration. So the torque about the center of mass is just going to be, assuming the radius of the cylinder is r, so F times r is going to be the moment of inertia about the center of mass, which is mr squared by 2 times alpha, which is the third equation. And finally we have a constraint. Just to recall what the question was, the cylinder rolls without slipping, right? So that provides another additional constraint to this problem, and to enforce that constraint we just use the equation. The acceleration of center of mass is r times alpha, right? So we have 4 equations. We don't need to solve anything because all we have to do is find the direction of friction, but let's just do a gut check whether this makes intuitive sense, right? So intuitively this cylinder is going to accelerate downwards in this direction, and its angular velocity is going to increase in this direction. So it's going to spin faster and faster, which means the direction of alpha is also as follows. And if we look at the torque about the center of mass, so the torque due to N and mg is going to be 0, but friction is going to produce a torque in this direction, and so that exactly matches our intuition of omega increasing in this direction, which means the angular acceleration is also in this direction. So that means I think all of the 4 equations we have written are correct, and the direction of friction we assumed is also correct. Alright, so right now let me just scroll up. So we know that when the cylinder is descending, friction is going to be up the incline, right? So that means option D is wrong because friction is up the incline while descending, and option A is also wrong. So it has to be up the incline while descending. So that means option A and D are successfully eliminated. So it's either B or C, which is correct. Okay, so now we have done the easy part, which is descending, which is what we are used to solving. Now let's focus on the, maybe this is going to be just as easy. Let's see. So let me scroll down a little bit. So now we need to find the direction of friction when the cylinder is ascending. Alright, so let me just clear these things off because I want to draw the free body diagram. Okay, so when the cylinder is ascending, we have similar free body. So that's going to be a weight mg, which can always be resolved into the mg cos theta component and the mg sin theta component. There is going to be a normal reaction that acts. And what about friction? So let me, similar to what we did here, let's think about what will happen without friction, right? Let's say there's no friction. So to find the direction of friction, the easiest thing to do is to think that there's no friction. So for a second, let's forget that there's friction. What is this cylinder going to do? Well, it's going to have a tendency to move upwards, right? Correct? So this is the direction of angular velocity, and that's going to decrease, but relative to the incline, this point is going to slip in this direction, right? So if friction is going to oppose the tendency of relative motion, and so it is going to act downwards, right? So that makes sense to me. Friction is going to oppose relative motion, so it's going to act in the downward direction. And so at this point it seems like we're almost done. So before I go ahead and tick down the incline while ascending and up while descending, I just want to draw the free body diagram or write down the equations similar to what we did here, just to make sure we're 100% correct. So this was the descending case, and let's write down the equation for the ascending case now. So in this direction, the acceleration of center of mass is 0, so n is going to equal mg cos theta. That's number 1. Okay, let me use a nice color. And we also know that mg sine theta, so in this direction the net forces are mg sine theta plus f. So mg sine theta plus f is m times the acceleration of center of mass, and that is going to be in the downward direction naturally. So that's number 2. And again, there's a third equation we can write using the torque equation. So the torque about the center of mass is the moment of inertia about the center of mass times alpha. So the torque about the center of mass is F times R, and that's going to be mr squared by 2 times alpha, number 3. And the acceleration of center of mass is going to be R times alpha, which is number 4, right? So the equations are essentially the same. It's just that the acceleration of center of mass is going to be in this direction, and alpha, the net torque about the center of mass, is in this direction. So alpha is going to be in this direction. Alright, and are we done? Well, I encourage you to pause the video for a second here. There's a reason I intentionally just took a second to ask you whether we actually did the right thing. So please pause the video now and see if you can figure out if anything went wrong here. So hopefully you're done pausing the video and thinking about this. It's very natural to think this way. So without friction, the cylinder is going to move upwards. So friction is going to act in the downward direction. And that is definitely a very intuitive way of thinking about it. But did any of you figure out what the problem is with what we did here? So if friction acts in the downward direction, the acceleration of center of mass is definitely going to be in the downward direction, which is fine. This cylinder is going to slow down as it goes up, which means it's accelerating in the downward direction. So this is correct. This is also correct. The acceleration of center of mass is going to be in the downward direction. Or I cannot say that the equation is correct, but what I can say is that the acceleration of center of mass that you get, the direction of the acceleration of center of mass that you get from this equation is correct. Okay, this equation is correct. All of these are correct magnitudes wise, but the problem is if friction acts in the downward direction, that would mean that the angular acceleration is in the same direction as the angular velocity, because this cylinder is going to spin in this direction, right? It's going to spin, but it's going to slow down intuitively. But the way friction acts now, it's actually going to speed up it's going to increase the angular velocity over time, because omega is in this direction. If friction acts in the downward direction, the angular acceleration is also going to act in the same direction. So omega is going to increase, and intuitively speaking, that is not how it works in the real world, right? If you roll a ball up an incline, the angular velocity is going to decrease over time, which means alpha was actually supposed to have been in this direction, correct? So what exactly went wrong here? Well, the weight always acts downward, so that was resolved correctly. Normal reaction always acts upwards, so that was also correct. So friction is where we made a mistake. Alright, so hopefully you realize the critical error that happened here. And just to correct that, I am going to scroll down some more and redraw the diagram. Yeah, let me just get rid of this. Yeah, let's redraw the diagram in maybe a different color. How about, yeah, this is a nice color. Okay, so so we had an incline, right? Inclined at an angle theta, and we also had a cylinder, right? Right, the cylinder was rolling up. Okay, so same thing, I'm just gonna directly resolve this. So there's an mg cos theta in that direction and mg sine theta in this direction. The normal direction in this direction. And remember, if friction acted in this direction, which is intuitively what someone might expect because the ball is rolling up, it would actually increase the angular velocity of the ball, which doesn't make sense. So that means friction would have to act in the opposite direction. Right, now let's quickly write down the equations. So n must equal mg cos theta, and remember this is for the ascending case, right? This is for the ascending case. So the omega was in this direction, but because friction acts in this direction, it is going to accelerate, the angular acceleration of the ball is going to be in this direction, which means omega is going to decrease over time, and that matches, what we expect to see in the real world, right? So this is correct, but let's just make sure all the equations check out. So n equals mg cos theta, mg sine theta minus f must be m times the acceleration of center of mass, and the torque about the center of mass must be the moment of inertia about the center of mass times alpha. So f times r is mr squared by 2 times alpha, and finally acceleration of center of mass is r alpha, which is the constraint for pure rolling, right? And this makes sense to me because it makes sense. We also know that the acceleration of center of mass must be in this direction, correct? Because the center of mass of the ball is going to slow down as it goes up, which means it's accelerating in the downward direction. Alpha now is going to be in this direction, which also makes sense because omega is going to decrease over time. And finally, we have the pure rolling constraint. And if you notice, the acceleration of center of mass and alpha are kind of in the same sense. That was another clue for us that we went wrong earlier, because the acceleration of center of mass was in the downward direction, while alpha was in this sense, which is kind of an upward sense, right? So that was another clue that we went wrong earlier. All right. So to answer the question, in the ascending direction, when the cylinder is ascending, friction is up the incline, and while it's descending, it's also up the incline, right? So the right answer is up the incline while ascending and descending, right? And when I first attempted this question, I found this very confusing because the descending part made sense to me because intuitively the ball is rolling down, so friction wants to oppose it, so it's going to act upwards. But the ascending case was really confusing. The ball is rolling up, and yet friction seems to be supporting it in some sense. So why is that? What exactly is going on here? So the answer is friction. Friction is very tricky. Let's acknowledge that first. Friction is very tricky, especially because this is static friction, right? Why is it static friction? Because the ball is in pure rolling. The bottommost point, always end up using a weird color. So the bottommost point on the ball is always instantaneously at rest. So that means the friction that acts both in the ascending and descending case, assuming it's pure rolling, is static friction. And static friction is always a bit tricky, right? And friction does not always act in the direction opposite to motion, right? Friction wants to oppose relative motion. And so to give you another example of how tricky friction is, so let's assume there are two blocks, okay? And if I were to apply a force on this block, and let's say this surface has some friction, and this surface has some friction. So intuitively, if the frictional coefficient is high enough, blah blah blah, this block is also going to move to the right. So this block is also going to move to the right. And so that means the friction on this block is actually going to be pushing it to the right, correct? The frictional force on the block on the top. So friction is actually aiding motion, right? So the bottom line is friction is really tricky. It does not oppose motion, but it really opposes the tendency of relative motion. Without friction, this the cylinder would not actually be able to roll, right? It would actually be translating. So in that scenario, friction might act a little differently. But because the cylinder is rolling, you would have to do essentially a free body analysis, similar to what we did here, to actually find the direction of friction. So I hope you found this video useful. And before we finish, I just want to leave you with one question, one thought experiment. So we did a harder problem where we considered pure rolling of a cylinder up and down an incline. But let me pose the same question if you had just just like a cube or a cuboid that was just sliding, that was going up the incline, sliding up the incline, and then down the incline. Okay, so the exact same problem as above. The cylinder goes up the incline, stops, and then rolls down the incline. But instead of rolling, let's consider a case of sliding. Okay, and my question to you is, what is the direction of the frictional force while the block is sliding up? And what is the direction of frictional force when the block is sliding down? And with that, I will see you in the next video. Bye.